Right. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Someone needs help on WhatsApp. Can you please reply for me? Right. So the topic that we're going to cover today is reaction kinetics. Okay, so we already did a little introduction to this topic where I asked you to plot a graph. Okay, it's a concentration over time graph. Okay, so you will see that the curve or the feature of the graph looking like this. And if you come across a graph, you really have to read the axis, okay? Because for this topic, there are two types of graph. The one that you can see here is the concentration time graph, concentration on the y-axis and time on the x-axis, okay? The graph that is being shown is the graph plotted for the concentration of products. How do we know that? Because at t equals to 0, initially, you start with 0 product, okay? You don't have anything, so that must be of a product. I'll show you the concentration time graph of a reactant later on. Okay, so what can you get out of this concentration time graph? This brings us to the next part, which is rate of reaction, okay? In your notes, on the first page, the very top box of your notes, it says that rate is a measure of how fast the concentration of reactants decreases or how fast the concentration of products increases. Or in a mathematical form, in an expression, we can say that rate of reaction is equals to change in concentration over the time taken. So change in concentration, if you look at the graph, concentration is the y variable and the time taken is the x variable, okay? To find the rate of a reaction, you can use a concentration time graph, and I hope you still remember this. Change in concentration is change in your y values over the change in time, change in your x values. So if you take change in y over change in x, that should give you the gradient. Okay, so this is just showing you how to find the gradient or the rate at different concentration of your products or at different time of your reaction. Okay, so in your AS syllabus, you already know that at the start of the reaction, the rate is the fastest. Okay, the reason for this is because you have a lot of reactants available to react, and then as the reaction proceeds, the rate decreases or the rate gets smaller, right? So this can be shown to you graphically. Okay, the rate is equals to the gradient, and as you can see, the gradient in this graph is decreasing. Okay, right. What else do I want to talk about? So, okay, this one I'll talk about the second type of graph, which is rate on the y-axis and concentration on the x-axis. Okay, this graph is showing you the concentration time graph of a reactant. How can you tell? Because look at the initial, at the start of the reaction. At the start of the reaction, you have about 1. How do I read this graph? 1.8 something mole per dm cube of reactants. Okay, so of course, over time, your reactants will decrease until it eventually reaches either 0 or it reaches a flat line, a plateau. This means that the reaction has stopped. Okay. Right. I think we've done this already in class. So the unit for rate of reaction is, if you refer back to the expression, units of concentration is mole per dm cube, and the units for time is seconds. It can be hours, it can be minutes. It all depends on the question. Okay. Right. So most of these things I have already talked or explained to you, but I need to just go through it again because we had like 2 weeks of break. Okay, right. So the rate of change of concentration is the slope or the gradient of a concentration time graph. Okay, the gradient at the start t equals to 0 will give the initial rate. Now you may think that at t equals to 0, the reaction, the rate is 0. Okay, when the question asks you to find the gradient or the slope at t equals to 0, this means that they want to know the rate of the rate of reaction just after t equals to 0. Okay, so this means that it is the initial rate of reaction. Okay, and as you know, this graph is also showing you nicely that the gradient or the rate is also decreasing. Okay, how do you know that? You look at the slope of your tangent. Okay, the rate of reaction at any time equals the gradient. Okay, the gradient decreases as the reaction proceeds, showing that rate is slowing down. The reason for this is nothing new. Okay, initially the rate is the fastest because of the higher frequency of collisions between reactants. So I've already mentioned this, that you have a lot of reactants at the start, so that's why your rate is also fastest. Okay, so I think you've already copied this down. All right, the steeper the gradient of the graph, the faster is the reaction. When the graph is horizontal, okay, when it reaches a plateau, a flat line, the gradient is 0. When your gradient is 0, that means rate is 0, the reaction has stopped. Okay, next one is the rate equations. I think I have also gone through this with you. Correct me if I'm wrong. Can someone confirm it on the chat box that I have explained the terms? Because otherwise I will just go through this quickly. Okay, so the rate equation for rate of reaction, the expression, okay, so I haven't done it. Right, so to write down the rate equation, okay, it is a little bit different from writing down the equilibrium constant. Usually equilibrium constant is equals to the concentration of products raised to the power of the stoichiometry divided by the concentration of reactants raised to the power of their stoichiometry or mole number. Okay, in this case, it's different, right? So I'm just going to explain the terms first. Rate of reaction is equals to K, which is your rate constant, okay, times the concentration of reactant A raised to the power of M, okay. Now this M is not your mole ratio, not your stoichiometry number, but it is what we call the order of reaction, okay. I'll talk about that later, times by the concentration of reactant B raised to the power of N. In this case, N is the order of reaction with respect to B. Okay, M is the order of reaction with respect to A. So when we talk about order of reaction, we always have to refer it to a particular species. Okay, which species we are talking about. Okay, let me just pause for a minute. Who am I missing? Ang and Iqbal. Okay, right. Going back to the order of reaction. So order of reaction can be zero order, first order, or second order. Okay, there are more, but for your syllabus, we're only going to cover 0, first, and second order. So if it's 0 order with respect to A, your M would be 0. Okay, if the reaction, the order is say 1, first order, with respect to B, so that means N here is 1. Okay, so how do we find the orders? We cannot find the order, the number of order. We cannot find it from the equation. You actually have to carry out the experiments. Okay, you need experimental data to determine if the reaction is 0, first or second order with respect to a particular species. Okay. Right. The next one is total order of reaction. Now, if we're talking about the total order reaction, that means you add up all the orders of reaction that appears in the rate equation. Okay. So for example, just now I said that M is equals to 0 and N is equals to 1. That means the total order of reaction is just 1. Okay. Let me try to annotate. So if M is 0 and then N is 1, so my total order of reaction for this particular reaction is 1. Okay. Other things that I want to talk about is the square bracket A. It means just like your other expression. Square bracket means concentration and the unit is mole per dm cube. Okay. Likewise, the same for species B. Okay, so A and B in this case is the species, either the reactant or the product. As I said, you cannot predict what appears in the rate equation unless you do an experiment and analyze the data. Okay, how to analyze the data? That's what I will teach you later on. Okay, funny thing, I cannot see my mouse, so you will see me scribbling because I cannot see my cursor. Okay, mouse. Okay, right. What other things that I want you to take note? Rate equation may not include all of the reactants in the chemical equation. Okay, it can include all the reactants. It can include some of the reactants. Okay, there is no particular rule unless you carry out the reaction. The orders have nothing to do with stoichiometry in balance equations. They are worked out experimentally. So I've already repeated this a couple of times. Don't forget, I've mentioned the units of concentration. The units of rate will be mole per dm cube per second or per minute per hour, depending on the question. Okay, moving on. This is just an example of rate equations for some reactions. Okay, you don't have to memorize them. I just put it in your notes as examples. If we look at the first reaction, we have hydrogen reacting with nitrogen monoxide to form steam and nitrogen gas. And the rate expression is equals to K. You will always have K because that's your rate constant, times the concentration of hydrogen to the power of 1. That means the order of hydrogen is 1. Okay, times by the concentration of nitrogen monoxide to the power of 2. This means that the order is second order with respect to nitrogen monoxide. The order is first order with respect to hydrogen. Now you can see that the order has nothing to do with the stoichiometry question. Yes, you may argue that the nitrogen monoxide has a mole ratio of 2 and the order is also 2. That is just a coincidence. Okay, so for this reaction, the total order of reaction would be 3. Okay. Next example. This time you have a nitrogen monoxide with a carbon monoxide and oxygen to form nitrogen dioxide and carbon dioxide, and the rate equation is equals to K, your rate constant, times by the nitrogen monoxide raised to the power of 2. That means it is second order with respect to nitrogen monoxide. Okay, so you see that in your reactants, you have 3 reactants here: nitrogen monoxide, carbon monoxide, and oxygen. However, the carbon monoxide and the oxygen do not appear in your rate equation. Okay, there is a reason for this, right? If you look at the rate equation, okay, you can see that the rate is proportional, directly proportional to the concentration of your reactants. Okay, so if you increase the concentration of your particular reactant, your rate should also go up. Now, the reason why some reactants don't appear in the rate equation is because they do not have effect on the rate. Okay, so this is what I will explain to you next, right? So the total order of reaction for this particular reaction is just 2. Okay, so this is an example where not all of your reactants will appear in the rate equation. So the thumb rule is that the species that appears in the rate equation are the species that affects the rate of the reaction. Okay. Last one, you have 2 nitrogen atoms combined to form a nitrogen molecule. Okay. The rate equation is equals to K, again, the rate constant. Nitrogen atom raised to the power of 2. This means that the reaction is second order with respect to nitrogen atom. Okay, coincidentally, it is the same as the mole ratio, but this is not always the case. Okay, times by the concentration of nitrogen gas, which is your product. Again, we cannot possibly predict this by just looking at the equation. There must be some sort of data from the experiment that helps explain why the product appears in the rate equation. Okay, so in this case, the reaction is first order with respect to the nitrogen molecule N2. Okay, the total order of reaction would be 3. Right? So the take-home message from this is there is no relationship between the rate equation and the chemical equation. So many times I have repeated this over and over again. Okay, next we are going to explain and use the terms rate constant K. Okay. Right, nothing much to explain about the rate constant K. It is a constant, and just like any other constant, K is constant at constant temperature. So that means if you start changing the temperature, your K will change. However, if you change your concentration, you change your rate of, you change your surface area, your rate constant will not change. Okay, so this constant is the same as equilibrium constant, where it only changes in value when temperature is changed. Okay, units of K depends on the overall order of reaction. It must be worked out from the rate equation. Okay, so the only thing that I want you to take note of this is how to work out the units of K. Okay, for a total, okay, so this one at the in this box on the right, basically I don't want you to memorize them because it's easier for you to work it out. Okay, so if you have a total order of reaction is first, so that means your units for K is s to the power of -1. I'll explain to you how to work this out if you don't already get it, but it's really simple. It works just like you work out other units. Okay, for a total of second order overall, your units is mole to the power of -1 dm cube, s to the power of -1, and then for third order is that. Okay, so how do we work this out? Let's see. Okay, let's use one of this example, and I am going to try to annotate this. Okay, right, so you know that the units of your rate is mole per dm cube per second. Okay, so there's your K, right? You want to find the units of K, so you have to move your concentration terms to the other side. Okay, nothing too difficult. Right, rate is mole per dm cube. It would be so much faster if I were to do this on the whiteboard. Mole per dm cube per second square. Okay, divide by, because I am carrying the concentration of hydrogen and the concentration of nitrogen monoxide terms onto the other side. So mole per dm cube, if you can see this already, these two species combined would have units of mole 3 dm minus 6. Okay, so in this case, I lost my cursor again. Right, there we go. I don't know why I am losing this cursor. Mole per dm cube. Oh my God. Oh, okay. Yeah, just cube it, because I have a total order of reaction 3. Okay, now seeing that, you can see how difficult it is for me to write things down. I hope you can work it out yourself. If you cancel this mole per dm cube and mole per dm cube, and then you bring that term up, you should get mole minus 2 dm minus 6, right? So sorry about that just now. 3 times 3 is 9, and I can't do math. You spotted my mistake. So, okay, please correct if you wrote down the wrong thing just now. When I cube my mole per dm cube, it should be mole to the power of 3 dm to the power of minus 9. Okay, I cannot math, so please forgive me. Right, so the unit of K will have that s to the power of minus 1 term. Okay, you know what to do. So I will just move on. So this works for any other rate constant as well. So you just have to move this concentration of nitrogen monoxide onto the other side and do whatever cancellations that you need to do. Okay, so that's why it's better for you to work it out rather than memorizing this box. Okay, moving on. Explain and use the terms order of reaction. So this is where something new for you. Okay, what? The meeting will end in 10 minutes. How come? Okay, let's see. I'll try my best. Right, explain and use the terms of order of reaction. So this is the big question that you're all asking. What is order? Okay. Right, order of reaction is that number that you raise to the power 2, okay, onto your species. So order of reaction with respect to a particular reactant is the power to which the concentration of the reactant is raised in the rate equation. So the definition of order of reaction is literally writing down the expression into words. Okay, how would you explain this power m and power n in words? Okay, so I will not dwell much into that. Now, how do you know if that species, if that reactant is 0 order, 1st order, or 2nd order? Okay. Now, before I talk about this, I would just like to remind you that in your AS syllabus, you saw that there are factors that affect the rate of reaction. Okay. One of them is concentration. If you increase the concentration, you say if you increase the concentration of the reactants, your rate of reaction will increase as well. Correct? Now, I'm going to tell you that not true, at least not for all, okay? Only increasing some reactants will, only increasing some concentrations of a reactants will increase the rate, okay? Right, so what's the lie? Okay, 0 order is the one that changes things. Okay, so this is a game changer. Zero order, if you look at the not definition, but the explanation for zero order, the concentration of A has no effect on the rate of reaction. Okay, so this means that reactant A, okay, I don't have any specific example here. If I increase the concentration of A, no matter by how much, my rate of reaction will not increase. It will not slow down, but it will just stay the same. Okay, so this is where you can start arguing this is not true. In AS, I learned that increasing the concentration of reactants will increase my rate. Okay, so zero order has no effect on the rate, no matter how much you increase the rate of reaction. Okay, so that means if we double the concentration of A is here is a reactant. Okay, the rate of reaction stays unchanged. So if I write that down in my rate equation, K is equals to A raised to the power of 0 because it is zero order. And I hope you can see that A to the power of 0 is 1. Okay, oops. So this term will become 1, and therefore your rate is equals to K. Okay, that's how you write it down. You can omit anything that has a zero order. You don't have to include it in the rate equation. Okay, next one. I have like 6 minutes left, so I'm going to finish off this slide really quickly. The meeting will end because we're all using it for free. So just be prepared for that. Okay, now for your first order, right? First order is the rate is directly proportional to the concentration of your reactant. So this makes sense. Okay, this doesn't really contradict our knowledge that our prior knowledge. So if I double the concentration of my reactant A, the rate of reaction also double. Okay, so if I increase the concentration of A, say, by 3, the rate of reaction will also increases by 3. So this is what directly proportional means. Okay, however, whatever amount I increase my concentration is, the rate will have the same, exact same effect. Times 3, rate goes up by 3. Okay, if I change it by 5, the rate goes up by 5. Right, so that's first order. The last one, where is my cursor? Is second order. For second order, the rate is proportional to the square of concentration. Okay, it's proportional like your first order, but it's not directly proportional. Okay, what do I mean by this? So if I double the concentration of my reactant A, the rate of reaction will increase by 4. Okay, why? Because increased concentration by 2, so the rate will go up by the square of 2, which is 4, right? If I increase the concentration of A by 3, for example, my rate will go up by 9. Okay, so that's what it means by the rate is proportional to the square. It means that whatever change or whatever effect to the concentration, the rate will increases by the square of that change. Okay, right. So this is the same effect if you were to decrease the concentration. Whether you decrease the concentration, the rate will also decrease. If you increase the concentration, the rate will increase. Okay, so for tomorrow's lesson, we are going to use the graphs to work out the orders. Okay, so now you already know what 0, first, and second order is. In the next lesson, we will look at the graph and how we could use it to determine your 0, first, and second order. Okay, so I'm going to unmute you all. Hello, everyone.
Hello, Miss.
Hello.
How was it? Okay.
Yeah.
Yes.
Okay.
Yes.
Right. Hold on. Let me just stop recording first. For those of